Michael, can you go share as a presenter slide? Right now, we can see your.
Oh, yeah. Let me make sure this just works really quick. Okay.
We are live? All right. Hello, everyone. Thank you all for coming to part 4 of the Celo Tech Talk series. I'm Judy Piper. I'm an engineering partner at Celo Labs. I'm currently based out in Berlin to lead and grow engineering team here. And I'm also the host for this Tech Talk series. One of the many Celo Foundation's efforts to share and spread the Celo technology knowledge with the Celo community. While the sessions are ideal for Celo developer community working on everything from mobile applications, distributed systems, blockchain, to cryptography, to infrastructure and networking operations, anyone who wants to learn more about Celo and how they can contribute to Celo community is welcome. And for those who missed the first 3 sessions, we have the recordings available on Celo Foundation's Crowdcast as well as a Celo YouTube channel. Last week, Tim Morton, a protocol engineering partner, gave an in-depth overview of Celo consensus and proof-of-stake mechanisms, which are at the heart of securing, scaling, and stabilizing Celo. And in today's session, Mike Straka, who joined here, a crypto engineering partner, will introduce us to Plumo, a new ultra-light client validation protocol, and how the team at Celo Labs is scaling Celo blockchain, syncing, and validation for resource-constrained mobile devices. Michael, can you please introduce yourself and kick things off before we kick things off?
Yep, thanks, Judy. Michael Straka, got involved with cryptography at a research lab at school at Stanford, and always had sort of disparate interests in things like economics and cryptography and social impact. And working on Celo has been a pretty cool way to combine all those things. And today we'll be talking about a light client we've been working on using snarks, which, if you don't know what those are, we'll get to that. And yeah, so it should be pretty fun. So I guess we can just get going. So what is Plumo? It is a sort of proof-based light client. And in particular, what is a light client? Why would we even want something like this? Well, a light client is just a way of, if you look at something like Bitcoin, which is very large, 260 gigabytes, normal user who just wants to send a transaction with Bitcoin, they're going to have a lot of trouble with that, because not only do they have to download all of that data, which can take a lot of time and storage space if you're not running a mining rig, they also need to keep up with the rate of new data that's being added to the chain. So even just keeping up with the chain can take a lot of resources. So ideally, you want to shorten the time that it takes you to verify that the chain is valid. And I'm assuming some familiarity with blockchain here, but basically you have a bunch of blocks chained together, and each block has financial transactions in it. This is a very simple explanation. And this is even more of a problem if you're using something like a smartphone, where you don't have 260 gigabytes of storage space to spare. even if that were something you could download efficiently, which you probably can't. So what are some ways of getting around this? Well, in the original Bitcoin white paper, there is something called the simple payment verification that Satoshi came up with. And what this basically says is that in a proof of work chain, Celo uses proof of stake, but if you're doing proof of work where you just hash the previous block and you solve some difficulty puzzle with each block, you can just verify that the hashes are correct, right? The sort of header of each block, and then later specifically verify transactions that you care about. And you can also do this with chains like account-based chains like Ethereum, as Bitcoin is UTXO-based, Ethereum is account-based, Celo is also account-based. So, sort of unit, like core unit of storage on chain is an account rather than a transaction. Becomes a bit more expensive, but it does reduce the cost of verifying the state of the chain. But you need to go and specifically verify certain transactions. So that's sort of a first approach. So for a proof of stake chain, so we are going to cover here, since we're using some pretty heavy duty cryptography. There is going to be a lot of background and preliminary information in this talk. So if you're already familiar with that, I apologize, but this is want to make this as accessible as possible. So even if you're not as familiar with the kind of things we're using, you'll still be able to get a sense of what's going on, and we'll be able to get some really interesting stuff. But it is going to take a little bit of time to get through it. But it will be worth your time. So what is proof of stake? So Celo uses proof of stake, and what that basically is, as Judy mentioned, Tim gave a great talk on this last week, which I haven't seen, but I'm sure it's excellent. He knows a lot about this stuff. You have a set of validators that are elected by holders of Celo, and the mechanics of voting aren't going to be important for what we're talking about right here. What is important is you will have some number, say 100, of elected validators, and each of those elected validators is going to sign off on blocks of transactions that they receive. And the assumption is that if 2/3 of validators or more sign off on a block, then the transactions in that block are valid. Because we're assuming that at most 1/3 of validators will be faulty or malicious. And then we can just run a consensus protocol on those validators to make sure they all agree on what they're seeing. So what sort of cryptography do you use? Well, we were just mentioning validators, and one of the more basic cryptographic protocols we use is a signature scheme, which you can just think of as a proof of identity. You run a key generation algorithm given some security parameter, one to the lambda, which you can just think of how you always want your scheme to be virtually impossible to break, but you can make it even more impossible by increasing the size of lambda, depending on how how cautious you want to be. And the key generation algorithm is going to give you a secret key and a public key, SK and PK, on the left here. And then you're going to have a signature algorithm that takes in a secret key and a message and outputs a signature. And that just proves that you have authorized that message. So each validator that we were discussing can sign off on a block to produce a signature on that block with their secret key that corresponds to their validator identity. And then if a signature is valid, it's been produced in this manner, then you can verify it with a verification algorithm, which takes in the public key corresponding to this secret key, the same message, and the produced signature, and will output 1 if the signature is correct. So it's pretty basic. Many of you there's a good chance that some of you are familiar with this already. We can complicate this a bit more with what's known as an aggregate multi-signature, which is just a fancy way of saying that we can combine several signatures into one. So in particular, we have the same keygen and signing algorithm as before, the same interface for those. But then we also have a multi-signature algorithm, which can take in multiple signatures and combine them into one. And similarly, we can combine several public keys into one aggregate public key, or APK. And then the verification algorithm will work as before. So as a more concrete example of this, I could go to my friend Alice, and we both want to sign off on the same message, and we have 2 different secret keys. So what we would do is sign that message individually to get my signature and Alice's signature. We would combine those 2 signatures into one to get a combined signature, and then we would combine our 2 public keys together. And then that resulting combined public key would verify against the combined signature for that message. So a bit more complicated of a concept is zero-knowledge proof. So we're not going to get too much into the internals of how these work, but right now we're just going to go over the high-level overview of how it works. So one way of thinking about a proof, and technically we don't use the zero-knowledge property in our light client because the information we're using is all public. We care more about being able to efficiently verify proofs. But one way of thinking about these kinds of proof systems is that you have a prover and a verifier. And they have taken effectively a problem or class of problems, R. And that can be something like, so in the US, we have what's called a social security number. And it's just a number that the government gives you that's tied to your identity. And so what you might want to do is give a proof that you know your social security number that identifies you, or say your credit card number, or whatever value that you might want tied to your identity. So then R here, the class of problems we're talking about, would be, do you know your personal identifier? Say social security number. And then we can think of X, which is a public value, which both the prover and verifier have access to, as a sort of value that parameterizes that set of problems, or rather, it selects a specific problem from this broader class. So X here might be your actual identity, say your name. Right, so for X for me could be Michael Straka. And then W here would be a satisfying input to the problem, or a witness. And in this case, it would be, say, just my social security number, which I'm not going to say out loud here because that would be very bad. But in a zero-knowledge proof, we could construct it so that W is not revealed to the verifier. So you could say, prove you know your personal identifier without revealing what it is specifically, but while revealing your identity, which is going to be X, because that's just necessary. So how this is going to work is that a prover produce a proof pi that they know is satisfying input for the problem they have, which is just described by R and X together. And then the verifier will output 1 if pi is a valid proof. And to get a little bit more technical, we refer to R as an NP relation. Technically, this is a bit of an abusive notation because R should be a set and not a function, but if you don't know what any of that means, it doesn't matter. It's just very subtle theoretical difference. So an NP relation is really just means it is a problem that can be efficiently verified. As in computer science, computational complexity, we just say that something, if it can be done in polynomial time, it's efficient. And NP just means something can be verified in polynomial time or verified efficiently. And the NP relation is just everything that is a sort of a satisfying input to that problem. Okay, so you can think of, do you know your social security number as being an NP? This is important because we need the problem to be efficiently verified to be able to do it in a snark. So, and some of you may have heard of snarks before. So let's cover those briefly. There are a lot of subtle different definitions between that you can give for snarks that do conflict a bit. You can even define it as a cute fuzzy animal. I've seen this at least once, but that's not what we're going to be talking about right here. The snarks that we care about, the acronym stands for succinct, which means it is small. The proofs are small and very fast to verify. For the system we use, it's a few hundred bytes, few milliseconds. So it's very efficient. Non-interactive, so there's no going back and forth between the prover and verifier. Argument of knowledge. And the knowledge property just means that we can prove mathematically that the prover knows W. And that can be a bit nuanced, but the intuition of the property is pretty simple. It's just the prover needs to know W. It's not enough that we just know that a W exists somewhere. So one of the main differences with a snark is that instead of taking in the whole NP relation, we run a setup algorithm which generates a common reference string, some kind of shared randomness that both the prover and verifier have access to. And then that allows us to make things much more efficient. And if in particular, some of you may have heard of sort of trusted setups or things like that, where you can do a longer multi-party computation ceremony to make the setup more secure. Because if just one person does it, then they have the power to, if they know the private randomness that was used, they can just kind of break the whole system. But if 100 people do it, then all 100 of them need to collaborate in order to do this. So it makes things much more secure. So this is going to be the most complicated thing we're talking about. If you don't understand it immediately, it's okay. Also, feel free to ask questions later if something isn't clear. But so to instantiate a snark, we use what's known as an elliptic curve. And what this is if you work with the, say, rational numbers that everyone knows and loves, and these are just kind of normal decimal point numbers without the all the irrational stuff like pi or square root of 2. It's just going to be a curve on a graph. And when we say the points on the elliptic curve, it's literally just the points of x and y coordinates that are on the curve. Right, so x is just horizontal coordinates, y is vertical coordinates. And we can represent a point G as just the xy tuple, right, of points. And then, since the curve is also what's known in algebra as a group, which is just a set with one operation, right? If you're going to sort of positive integers or integers, because if you do too much math, your brain kind of decays a bit, and you're not able to talk about numbers anymore without saying things like positive integers. If you look at integers, it's 1, 2, 3, 4, or 5. You have addition and multiplication. That's 2 operations. If we restrict them just to addition, then that's what's known as a group, because we just have one operation. So elliptic curves, we only have one of the 2 of addition or multiplication. But just to make things more complicated, sometimes mathematicians call it addition, sometimes they call it multiplication. It's actually the same operation. This is only one operation we do to add elliptic curve points together or multiply them together. But addition and multiplication here are the same thing. Normally people call it addition. So if we add 2 points together, say the same point G to itself, we get 2 times G, and we get a new point on the curve. And it's not important exactly how that's done, but we can do it. And similarly, A times G plus B times G gives us A times B times G. Then in order to actually define an elliptic curve for cryptography, because we want things to be harder to work with for an attacker, we use finite fields instead of the rational numbers. Say f sub p, which is just the finite field of order p. When we say order, that's just the number of elements in the field. And in particular, it's just going to involve addition and multiplication modulo p. Modulo is just, if you think of hours in a day, those are modulo 12 or 24, depending on what system you use, because it just loops back around at the end. Right, so 3 plus 12 is just going to be 3. And this is going to look a bit messier geometrically, which is fine because you would never need to visualize it anyways, but it's not really going to look like a curve anymore, but we still say that the points there that are sort of, we still call them as being on the curve. Right, and then G itself is the elliptic curve, big G. That's also going to have an order, which we denote by the little brackets around the symbol. And that's going to be Q. So the elliptic curve is going to be a cyclic group, and what that means is that it also loops back around if you just keep adding an element to itself. So in particular, if you add G to itself, or G is a point in the curve, Q times, then you'll just get back the identity point, which if you add, say, G and 1 together, you just get G. Right, so, and then we call the, so if you notice, we can do, if we add points together, we can do operations in the exponent of G. And the place where we do those operations, we call the scalar field. And that's just going to be the field of size, finite field of size Q. And it's going to be very similar to the base field FP, except instead of being of size P, it's of size Q. Instead of using P as a modulus, it uses Q as a modulus. Now, this is a bit complicated, but one way of looking at this is that in software, we have a lot of, we care a lot about making abstractions between how something works, how it can be used, and implementations. So we can think of the base field FP here as implementing the curve, right? When you actually go to do the elliptic curve operation, you're going to be doing computations in FP, addition and multiplication. But when you actually go, what you want to do when you are doing these operations is to do calculations in the scalar field in the exponent of the curve, which is going to be an FQ. Right. Even though when the operations are actually executed on whatever machine you're running, everything is going to be running FP operations. And that's going to be important later. So the last bit of background knowledge, how do we actually sort of engineer a problem for a snark? We noticed earlier we had an NP relation R that we need to summarize in a common reference string in order to have the whole thing work. So how do we actually get our how do we design it in a practical system? In practice, we engineer this as an arithmetic circuit, which arithmetic circuit satisfiability is NP complete. That just means we can reduce any other NP problem to it. Right, sort of in the same sense that most programming languages are Turing complete, so you can express any computation in that language. Well, here we can express any efficiently verifiable problem as an arithmetic circuit. In particular, this is just going to be a bunch of addition and multiplication gates, and these are going to be done in a finite field because, in cryptography, we love finite fields so much we do everything in them. Partly because there are, hard problems that we can reduce the security of certain schemes to. So if you'll notice earlier, I mentioned that we have a base field and a scalar field when dealing with an elliptic curve. The elliptic curve is implemented by the base field. So it's performed when the operations are performed, but the scalar field is sort of the end result of doing computations with the curve, right? It's what we want to do. And because of that, when we define an arithmetic circuit for a snark, we want to define it over the scalar field of the elliptic curve. Because we're going to be, a lot of these snark protocols, they're done in the exponent of an elliptic curve. And that exponent is where we're going to represent the arithmetic circuit, right? We can reduce it to some other problem that's more sort of algebraically convenient, that works out better there. and just execute the proving and verification algorithms in the exponent of the elliptic curve, which is the scalar field f sub q. But when we actually go to those computations, we'll be doing FP computations, because that's how the curve is implemented. And that'll become important later when we're discussing doing signatures inside of snarks, which is an important part of our system. Okay, so that's just preliminary knowledge. So how does what we're doing differ from related work? Well, there's been solutions like NepoPow, Fly Client for light clients, but those sort of rely on statistical properties of proof of work hashes, and they don't really apply to proof of stake. You could have maybe every 100 blocks you get 10 times as many zeros. I'm just making this up. And then you can make verification more efficient based on that. But we don't have proof of work, in our context that we're talking about, we don't have proof of work difficulty puzzles. So that doesn't really apply. There's also been some very interesting work with Coda, where they verify their entire blockchain protocol in a snark, including transactions, consensus, everything in one snark proof, which is very efficient. So that's very good. And they even do proof recursion, which means that not only do they have proofs, but they have proofs that prove every previous proof that's been done. Sounds a bit magical, but you can do it. So this is kind of, in some sense, this is the ideal solution for the end user, because they only need to verify one proof, but you need to do a lot of little hacks with the consensus protocol to get it to work with a snark, and it also rules out some other functionality you might like smart contracts. And if you just use the simplified payment verification assumption, where you assume there are full nodes on the network that are going to verify the state of the whole chain, and you're just going to worry about verifying specific transactions for your light client, then you can get similar efficiency with a lot less work, and not just work in terms of implementation, but also in terms of sort of needing to use larger curves, or issues of sort of proof availability. You need someone to be constantly generating these proofs. So this is something we decided not to go with. And what is our solution? Well, like we said, we could use the simplified payment verification assumption pretty much by itself. And say you're looking at the chain with a smartphone, and you just verify each header, the validator set in each header is correct. Is what the SPV assumption means for proof of stake is that you only verify that the validator set is correct, and that they signed off on each specific transaction that you care about. And this is okay, because if you're assuming that 2/3 of the validator set is honest, which we need for security anyways, then this is fine, because the validators themselves will make sure that all the transactions are correct. And in addition, so for a bit more context, with Celo, there are epochs. Each epoch is 1 day, and every epoch, so every day, there is a new validator election. The validator set can change, and then each block is going to contain the difference of the validator set. Right, so if 2 validators get changed up, right, other validators get elected in their place, then that means that those 2 public keys of those validators are going to be in the next epoch header. So we can just check those, one by one, check all of the headers and verify the BLS signatures in them. And we discussed aggregate signatures, multi-signatures earlier. Those are also used. So each epoch block has, say, 100 headers, or 100 up to 100 public keys for validators, and they're going to have one aggregate signature that at least 2/3 of the validators have signed, and there's also going to be a bitmap that just describes which specific validator signed each block. So in order to verify the signature, you just go through the bitmap and combine the public keys of each of each validator that has signed that block according to the bitmap, and then the resulting public key should verify against the aggregate signature that is in the block. Right. So that's what we mean when we say epoch-based syncing. And then the magical part that makes us a lot more efficient is we can do all of this inside of a snark, right? Just verifying the validator set. So you can verify that the validator set is correct inside of a snark proof. So per epoch, what we basically want to do is to confirm that we are at the next epoch from the last one, that the sort of epoch counter has been incremented by 1, would be one way of saying it. And we also want to confirm that the bitmap in the block has at least 2/3 validators flipped on, and the validator is going to be switched to 1 if they sign that block, and that the aggregate multi-signature verifies against the combined public key from all of the validators who have signed who are in the bitmap. Good. And this is what's just described here. Oh, and you check this multi-signature against the block, minus the bitmap and signature itself. And then we can also make this a bit more efficient by doing sort of batch verification of BLS signatures. Not super important, but kind of interesting because we have 1 multi-signature per epoch block. So we can just combine those into another final signature, and then because it's over different messages, do a slightly more complicated batch verification. And we get some more efficiency from that. So we discussed proof recursion earlier briefly. What would that look like here? Well, with each epoch, we would generate a new proof. And then the next epoch, say we generated a proof at epoch n, then we go to epoch n plus 1. We can generate a proof pi that attest to the validity both of that specific the validator set at the new epoch block and the validity of the previous proof. Right, so we mentioned that snarks can be done for problems in NP. That's any efficiently verifiable problem. Well, verifying a snark proof, that's efficiently verifiable. Of course, that's the main reason we use them, is because they are efficient to verify. So then, of course, you can verify snark proofs inside of a snark. And if you think about what that means, you can actually just verify all of the epochs. You can have n proofs, but only verify the last one, and it'll attest to the validity of the n minus 1th proof, which attests that the n minus 2th proof, n minus 2nd proof, is valid, and so on until you get to the very first proof. But there are some technical reasons you might not want to do this, such as the size of the curves are roughly twice as large as the curves you could otherwise get away with using. There's been some very recent work to sort of get around this, but it's still I think, a bit in the prototyping stages and being worked out. So to go with something a bit more, more efficient and reliable, we went with what we could call an inductive solution. And what I mean by inductive is just we have a chain of proofs instead of just one that's being continually composed recursively, and you just kind of verify each proof in succession. So you would verify the first proof, second proof, then third, then fourth. But the reason this is okay is because in practice, we're not actually doing one proof per epoch. What we're really doing is verifying a lot of data, say it could be 3 weeks, could be 3 months, could be 6 months, right? You could do any of these numbers, right? You could do 180 epochs per proof, or as many as we can fit in. And the proofs are all going to be the same size, same efficiency to verify, more or less. So, if you combine this with checkpointing, so you generate proofs for every 6 months and you checkpoint every year, then you only need to verify at most one proof at any moment. If you do, say, 3 months, then with checkpoints at 1 year, that's, say, 3 proofs at most. And then you can also get a bit more creative with this, where maybe you have a proof for 6 months, then another proof for 3 months, and another proof that fast forward you 2 weeks. Right. And then it takes you to a point where you need to manually verify 2 more headers for 2 more days. Right. So you can kind of, in some sense, you can fast forward an arbitrary amount of time with one single proof. So we mentioned we use BLS signatures. Slightly. So for the rest of this, we're going to get into some performance numbers later, and before that, we're just going to get into a little bit more detail about some kind of interesting technical details of Plumo. BLS signatures to sign, you just hash a message and then multiply it by your secret key, the result. And multi-signatures and key aggregation is just you add each signature and public key is going to be an elliptic curve point, and you just add them together to get the final signature or final public key. And then you can verify combined signature against the combined public key. In particular, this is what verification looks like. E here is called a paren. It's bilinear, so what that basically means is that you can verify if sort of the exponents of both elements on the right multiplied together are the same as the exponents on the left multiplied together. And basically all you're checking here is that G to the X is the public key, so X is the secret key. So we would expect that the signature on the left is just H, the hash of M, but exponentiated by or multiplied by X. So if it was signed correctly, this is going to verify okay. Right. Because sigma here on the left is just H of M multiplied by X. And then because pairings are bilinear, you're just checking if that exponent there is the same as what G is multiplied by, if it's X. And this is a bit important because we're doing verification inside of an arithmetic circuit, and this is a bit expensive if sort of with a normal cryptographic hash function that you might want to use. Because H here isn't just a normal hash, it's a cryptographic hash, which is a fancy way of saying that it's really complicated and hard to, it's hard to find, given H of M, it's hard to find M. You don't necessarily know what was hashed given the hash. So something else that's kind of clever we do is using a 2-cycle of elliptic curves. And I think we're running a bit low on time, so I'm just going to speed through this. It's going to be, this is a bit complicated, so yeah, don't feel bad if you don't pick it up the first time. But basically, we use curves such that the scalar field of the second is identical to the base field of the first. So that in particular, when we go to do computations in a circuit for the second curve, SW6, we're going to do those in the scalar field. That's going to be our arithmetic circuit computations. And since that's identical with the base field of 377 on the left, that means we can do 377 operations inside of the SW6 arithmetic circuit very efficiently. All right, because the scalar field of SW6 is identical to the base field of 377. Right, because if we didn't have that, if we just used 377 and tried to verify a signature over it inside of the scalar field of that curve, we're going to have a mismatch between the scalar field, the sort of abstraction that the elliptic curve provides, with the base field, which is the implementation of the elliptic curve. Right, it's like you're trying to do assembly on the wrong machine. Right, ARM instructions on a machine that doesn't support ARM, or something like that. It's not supported, and you can try and emulate the different field modulus, but it ends up being very slow. You get a logarithmic blow up in complexity, which is bad with respect to your whatever prime you're using. So effectively, we just do the entire proof inside of SW6, but we do signatures in 377 for that reason. Of course, we do verification inside of SW6. And then we mentioned doing a hash inside of the circuit, and basically make this short and sweet. We can do an algebraic hash that doesn't give us the randomness that we would want from the hash, but it makes the input y shorter. So that when we do a regular vanilla cryptographic hash like SHA-256, it's going to use up a lot less constraints in the circuit, and it makes things more efficient. Whereas algebraic operations, because that's all you do in an arithmetic circuit, is addition and multiplication in some finite field, that's going to be a lot more efficient. So compressing the input that way is a great idea, and it works. And then there are some also newer hashes with that are purely algebraic, but they're still kind of undergoing review. All right, so how efficient is our system? How efficient is Plumo? Well, as you can see, we ran this with a number of different validators on epochs, and turns out to take a few hours with, say, if you're doing 6 months of data, it's 180 epochs with 100 validators. It's going to be a bit expensive, but it's still not that bad. In particular, we rented one of the most largest, most powerful machines we could find on Google Cloud, and it took like a few hours. I think it's like 6 hours. $6. It's very cheap. And then memory consumption is also pretty high, but again, if you just rent a machine for a bit in the cloud, it's fine. And if you only generate, you need one person to generate these proofs every 6 months. That is I think, a perfectly reasonable assumption, even if you're just relying on goodwill. For verification, we also ran this on a number of different mobile phones. Even for the worst possible phone we could find. And when I say worst, I just mean slowest. I'm sure it's perfectly functional and fine if for certain things, but it was a little bit slow, but it still only took 6 seconds to verify, which compared to what it would have been for just verifying everything manually is pretty great. And then faster phones were just a fraction of a second. And then also, if you care about interchain operability, you can verify proofs in smart contracts pretty efficiently too. Cool. So I think now I'll pass it over to Judy. She can talk a bit about the next talk that's happening, and then after that, we can take some questions.
Awesome. Thank you, Michael. So next part of the Celo Tech Talk series will be on stability protocol. After Celo mainnet launch, and we enabled Celo a native protocol, and also through the governance process, Celo Dollar was enabled and is live now. And so Roman Grossman, who is a protocol economics partner, will give an in-depth overview of a Celo protocol, Celo stability protocol, and as well as Oracle and how Celo reserve is managed. So that's coming up on July 16th. With that, we'll take a Q&As.
Cool. I think we already got a question from Jeff, just about Plonk versus R1CS. So the system we were just describing with arithmetic circuits, that's also roughly equivalent to a problem called R1CS, where you just kind of multiply vectors together. You kind of just represent the circuit more algebraically in a way. Plonk is a newer system that's universal. So the nice thing about doing a universal snark is that we could do, right, we discussed doing epochs at different sort of lengths of time. Sorry, proofs for varying numbers of epochs. Right, so if you use like a normal snark, which doesn't have this sort of universal reference string property, then that's going to take the same amount of proving time for each length of epochs. So if your max is 6 months, each length will take sort of 6 months of proving time. Not literally 6 months, but how long it would take to do a proof for 6 months of data. Something like Plonk, it would sort of be more variable depending on how many epochs you're using. But that's not, it's not something we've looked at sort of empirically yet, how what the relative efficiency trade-off there would be. Because there would likely be some loss of efficiency as well, just in the general case.
We have another question on the Ask a Question tab. Jose asked, any validator can generate the snarks proofs, or is a specific one chosen by consensus?
So right now it's just that anyone can generate a proof, just literally anyone, and then you can just gossip that through the consensus protocol. So yeah, a validator can generate the proofs. It doesn't have to be, you don't need to choose a validator to generate the snark proof. It's just as long as it verifies correctly, that's all that really matters.
All right. Do you have any other questions on today's session, or other questions regarding Celo Tech Talks as well? And do you have any question for Michael? All right. Well, thank you everyone for joining, and thank you, Michael, for giving this talk.
Of course. Thanks for all your time.
Okay, thank you. Thank you all. Cheers.